I went to school here and it was on quarters, and I went to UC San Diego, which is on quarters, because all the UCs are on quarters except for Berkeley. So I'm used to quarters. They move fast, but it means if a class is really annoying, it's done in 10 weeks. So, and some of these are actually pretty annoying to teach. You wouldn't think that necessarily. That maybe you would actually, based on the reactions of your professors to various classes. I cannot be specific about that. I don't know anybody. I started here under Zoom and I remember nothing. I basically don't know anyone anymore. My professors who worked here, who taught me, the last of them is retiring. So I guess I don't know anybody. I'm the same as everybody here that like started their college under Zoom, which is I have an office. I'm lucky that the guy across from me I went to college with, so I know him and basically nobody else. So. It was weird. It was definitely weird being a Zoom teacher though. Like, I guess is what I do is I post YouTube videos and then they pay me every once in a while. Okay. So I guess it's time to start. Yeah. Okay. So the first thing I want to talk about is at least my sort of tentative idea here is that these are going to be what my office hours are. I have time to have office hours on Friday, but I don't know when I'm going to put that yet. I don't teach on Fridays, but I have meetings that haven't I'm trying to juggle the fact that I have like multiple graduate meetings with graduate students and other things going on Friday. So I will put something on Friday eventually. I just don't know when yet. Okay. There's also a possibility that if people cannot meet me over, it's always worth taking the time. So I shouldn't tell you this, but I'm going to anyway. So between say 10 and 2 on pretty much any day of the week, if you want to like have a quick Zoom call about something that you're stuck on and you think it's going to go beyond like having to do something in Slack, you can just send me a message. And if I'm available to make a quick Zoom call, I'm happy to do that. I have the ability to do math or whatever over a Zoom call. In my office, I can write on the board. So if you want to ask for that because you just can't make the office hours, feel free to ask. It's okay. Think about it as like sort of an appointment, except if I'm at my office and it's not in the middle of interrupting something, I'm usually capable of answering the phone. I mean, the phone in the Zoom sense. I have an office phone, but it's never rung once. So I'm sure it's full of messages about my car warranty. Okay, if you can't make any of these and you're desperate to have an alternate time when you can, talk to me and maybe I can try to make something work on Friday. Okay, I'm trying to schedule around 35 students. It's basically impossible. So I'll do the best I can. Any other questions about anything administrative before we proceed? All right. Okay, so we're going to start chapter 2.1 today. We're going to do enough of it that you guys are going to be capable of doing homework. So we're going to start, I think last time we sort of set up the idea that we're studying functions in several variables. And so I want to, because Polly is going to use some language around this for the rest of the course, and because I am as well, we're going to start with a little bit of vocabulary, including a term you may not have seen before. So functions in several variables. And by several, I mean 2. Almost always, I mean 2 variables. Okay, so function is atrociously written. Functions several variables. Almost always mean 2 variables. Okay, so a function has 3 parts. I have to tell you what it eats. I got to tell you where it spits the values out, and I have to tell you the rule that it uses to do it. So part 1 is I have to tell you a domain. The domain set denoted X is the set of inputs. 2. Now I know everybody out here is thinking, oh, he's going to say range. I'm not. I'm going to say codomain instead. Codomain. set Y. That's the set where the range lives inside of, right? So normally when we're thinking about a function, say from calculus, we think about functions that map the real numbers into the real numbers. They might not hit all the real numbers, but I'm telling you the inputs are real numbers and the outputs are real numbers. But I'm not telling you the range. I'm just telling you where the values pop out on the other side. That's why we use the word codomain here, okay, instead of range. And then 3, a rule of assignment. So normally what I mean is, if you give me an x, I better be able to produce a y, which is equal to f of x, whatever the rule happens to be. Now, because we're in vector language, really we should be doing these properties. When I write the rule of assignment, y is equal to f of x, what you should really write is y is equal to f of x. Because the set y doesn't necessarily have to live in the reals. It could live in some vector space. It could live in Rn. It could have a function that takes in 3 variables and spits out a vector with 4 components. Okay, so this could be a vector and this could be a vector. For us, usually, our functions will be functions from R2 into R. So we're going to be looking usually at functions that take in 2 elements and combine them together with some sort of rule and then spit out 1 real number as the output. Okay? Almost everything we do is going to be that. If you like, that means secretly in the background, almost everything we do is going to look like z is equal to f of x and y. That's the model you should have in your head. But this language describes way more complicated situations. Okay, now the range. I'll give you an example here. So you can define the function f from R2 into R by f of y is equal to x squared plus y squared. That's an example of the sort of function I'm talking about. If you want an example with some more beefed up domain range, you could write a function that takes R2 into R3 by f of xy is equal to the vector x plus y, x minus y, x squared plus y. That takes in 2 real numbers and spits out 3 real numbers. Okay, so when we talk about vector valued functions, this is the sort of thing that we could also describe with the same language. All right. So the range of a function which is contained is a subset of y. So it's a subset of the codomain. And it's defined to be the set of outputs. So the range of f is equal to, I'm going to use set notation here. It's the set of all y's in the codomain that are reached by something in the domain. Right, so the range is just what could come out. Now you've spent probably the last 4 or 5, 6 years of your lives computing ranges of things like paraboloids. But it's worth pointing out, as a concrete example, if you had something like f takes r to r by f of x is equal to x squared, if you were going to define all the pieces in the language we're using here, we would say that the domain of f equal to all real numbers, the codomain of f is equal to all real numbers, but the range of f is the set of numbers starting at 0 and going to infinity, because we can only hit while the outputs are all real numbers, we don't get all of the real numbers as outputs. We only get the y values between 0 and infinity. Okay.
I have a question.
Sure.
Why x is a vector but not y?
So I would just, everything should be vectorized. I'm trying to be consistent about this, right?
Okay.
In these definitions, things are vectorized and we'll restrict them to the scalar versions when we need to. Okay. Okay, now this isn't going to come up immediately, but it's going to be important later in the class. I have to write a couple of technical definitions related to if functions have unique outputs. Okay? So you guys remember the vertical line test tells you if a function is a function. The horizontal line test tells you if a function is one-to-one, right? So we have to introduce the idea of one-to-oneness and onto-ness here as well. Or if you like the high-level mathematical language, surjective and injective functions. So a function f in a space x to a space y is called onto or surjective with every element of y, every element in the codomain. Codomain y is also in the range. So onto means whatever the codomain is, you get all of it, right? The function x is onto or surjective. Every element in the codomain is also in the range. An example of a function that is onto is something like y is equal to x to the third. Because every element in R is reached by f of x. Yep.
When you're done with 1 to 1.
Okay. A function from x to y. Wait, this isn't suddenly going to devolve into proofs. We just need these are technical things that we need for certain statements we're going to make about differentiability later. The function f from x to y is called one-to-one. Probably uses what I think is the absurd 1-1 for one-to-one, but there you go, one-to-one. A function f from x to y is one-to-one if each element of the range comes from precisely 1x in the domain. It's in the range, only a single x produces it. And there's a algebraic condition that often gets used when you're talking about functions being one-to-one, which is that if x1 is not equal to x2, then f of x1 is not equal to f of x2. So it's sort of an algebraic way of checking to see if a function has distinct values. If the inputs differ, the outputs differ. Anybody got an idea about a function that happens to be, we're not going to do this right now, but what is a function that's one-to-one and onto called? Bijection, right? So bijective or? Or invertible, right? It's an invertible function. So when you guys have, in the past, when you studied things like the inverse trig functions, and they do that thing where they restrict the domain, the reason you're restricting the domain is to make sure the function is both one-to-one and onto, so you can actually take the inverse. Right? Okay, what was your question, Connor?
I remember the
All right,
It
then I will live in mystery.
was what's being formally provided. I think it's one-to-one correspondence.
Yeah, correspondence. It's the bijective correspondence or one-to-one correspondence. It depends on the field that you happen to be working in. Okay, so let's look at our favorite example here again. F takes R into R by f of x is equal to x squared. Is x squared onto or one-to-one or neither? Well, it's neither, right? It's not 1-to-1 because, for example, f of 2 is equal to f of -2. So two different x values produce the same y value, right? So it's not, it can't be 1-to-1 because the outputs aren't unique. Not 1-to-1. Is it onto? Oh, I just wrote it was onto over there, didn't I? Okay, so it's not onto because the range of f is equal to the values from 0 to infinity. Now, one trick that comes up a lot of times in which is not R. So a trick that comes up sometimes when you want theorems about different derivatives and integrals to be true, we're going to use this in here. And the same thing when we want inverse functions to exist is we can cheat and say, well, fine, it's not 1-to-1, but what if we just changed it so we only looked at it on half of its domain? So I'm going to write a different function down. It's going to look like the same function, but it's different. F takes 0 to infinity into R by f of x is equal to x squared. Remember, a function has three parts: domain, range, and rule. And if any one of them is different, it's a different function. This is not the same function as this one because its graph looks like this. And that graph is 1-to-1. Any input produces a unique output. This is a 1-to-1 graph. It's still not surjective, but it's 1-to-1. Now you might think, okay, can I cheat and restrict the codomain to the range? And the answer is yes. You can cheat again and make this function effectively 1-to-1 and onto. But normally the rule is if we want to make a function invertible, the game that we always play here is we cheat on the domain and replace this function with a different function with a better domain. So domain fixing is kind of part of the deal. All right. Okay, you can imagine it's much more difficult to be 1-to-1 and onto if you're a function from R2 into R and you're some sort of surface that's wiggling around in three-dimensional space. There's a lot of more places where like you're not going to be 1-to-1 necessarily, right? If this thing wiggles, heights are going to show up over and over again all over the place. Okay, where was I at? Surjective functions, not ontoness. That was page 2. Okay, so let's write down some more interesting functions than this. This is boring. X squared. Come on. It's a 300 level class. Let's get some good functions. So Polly's got like a million of these. I'm going to write down 2 of the most interesting ones. So let's look at this function. So let L of x, which takes Rn into R, be the length function. That is, L of a vector x computes the length of that vector, just using the distance formula. Is it okay if I write the distance formula that way with the sigma notation? Okay. I just mean take the entries of x, square them, and add them all up and take the square root. It's regular distance formula, right? That's a perfectly good function. Yep.
Are we going to use like with the absolute value symbols, are we going to use the double layered one and the single layered one? Or can we...
We are not. When I'm trying to emphasize the fact that I'm looking at vector lengths, I'm going to try as much as possible to use double. Like it's typical in math, like in math courses like this, if these things have different meanings to say what the meanings are. When I'm talking about the length of a vector, I'm going to try to talk about double bars, right? Because double bars apply to things that aren't regular old distance formulas, right? If I take single bars, I'm usually referring to the absolute, in this class, an absolute value of a scalar. Now that's annoying because there's other classes where single bars refer to the distance formula of things in Rn, and double bars refer to norms of matrices or norms of functions or something like that. I know it's different. For us in here, double bar is going to be chosen because we're trying to work on a broad family of things that are considered vectors. And I want to stay consistent with Polly, and she uses the double bars. Okay, is that function 1-to-1? This is a function that you feed it a vector and it spits the magnitude out. Pretty badly not one-to-one, right? Like L of the vector 1, 0, 0, 0, 0, however many zeros there are, the length of a unit vector, 1. By the way, this vector is usually called E1, the first standard basis vector, a vector that has a 1 in the first spot. But this vector also has length 1. 1 in the second spot, zeros everywhere else, also length 1. So pretty horribly not one-to-one. Is it onto? Is it possible to produce any number in R with this length function? Why not?
Because you're squaring all.
Yeah, you square things and then you take a square root, right? Negative numbers can't come out of this. Even if you believed you could take a square root of negative numbers because, you know, complex numbers are better than real numbers. You still squared all these things, which means any negatives that were present in the problem are gone, right? So you added a bunch of positive numbers, you take the square root. So this is not one-to-one because two different inputs produce the same output, and it's not onto because it can't be negative. Which means I guess the logic I want you to have in the back of your head about this is functions that are one-to-one and onto are functions that when you apply them, you keep all the information about the inputs in some sense. You haven't destroyed any information. If I have a function that's one-to-one and I look at an output, I know exactly where it came from originally. The length function basically destroys every piece of information that exists about a vector except how long it is, right? This is not an undoable function. It destroys tons of information. It destroys angle, it destroys individual entries, and what it spits out is, oh, here's how long the vector is, which is a great function, but not one that you can undo. Oh, here's another really good one. Exotic functions are fun. What does this one do? Here's a function. N takes R3 into R3. So here's a function that takes in a vector and spits out a vector. And here's what its formula is. What does that do? Oh, I guess I need to be careful here. N takes R3 with the exception of the origin and maps it into R3. I can't put in the vector 0, 0, 0, 0 because I can't divide by 0. So I just throw that out of the domain. I'm not going to allow myself to divide by 0. What does that function do?
Unit vector.
Yeah, I started like a lot of people say unit vectors. Okay, yes. So this is N for, this is the normalization function. It takes in a vector and it spits out a unit vector. Perfectly good function, actually continuous function. I can't graph it. I mean, I don't know how to graph from R3 to R3, but it's a perfectly good function. Very nicely behaved in a lot of ways. I did not say that in a way that was even remotely readable. So takes in a vector as an input, produces a vector as an output, where the output vector is the normalized or unit vector version of the input. One-to-one? Well, no, any vector pointing in the same direction is going to produce the same unit vector, right? Onto? Well, there's a whole lot of vectors in R3 that are not unit vectors, so it can't possibly be onto. So this is not one-to-one, and it's not onto. In fact, most functions fail both of these properties. Right? So when we get one-to-one and onto, it's pretty special. Mostly the point of these examples is to try to give you guys the idea that we have this entire family of things that we're describing with the language of this class that go beyond just regular old functions of calculus, right? That we're not just studying a language that works on curves and surfaces, but also handles stuff like this. All right. Okay. So that's the sort of base language we need. Now we're going to actually do some things. So we're going to visualize functions. And when I say we, I mean, I'm going to do it on the board, and then you guys are going to go home and making sure that you don't run away to Wolfram Alpha or Desmos, you are going to draw functions from R2 into R3, and you're going to pretend as hard as you can that you're not going to look at what the answer is in Desmos before you start. Okay. I mean, obviously you will, but there's going to be things that there's going to be things that in this approach, even if you start in Desmos to get an idea of what the surface is that you're looking at. And I actually, I'm going to countermand myself here because I was joking, which is if you want to understand what's going on with a function or an example we've talked about, you should go visualize it. These things are very difficult to compute by hand in many cases. And the visualization is the entry point to understanding what a function is doing. Because a lot of the features we're going to study don't show up on a Desmos or a Wolfram Alpha visualization. If you guys really want to go nuts, you all have access to Mathematica, and you could actually do really advanced things that we're going to do in here in the Mathematica language pretty easily if you want to download it. So you can code this stuff where you can look at things like contour lines or the vector fields that we're going to be studying, or the flow lines of vector fields. Like all this stuff is visualizable in a computer in a way that's about 1,000 million times easier than trying to do it by hand. And it's as annoying as it is to have to code it, it's way more powerful than Desmos, which is amazing but limited. All right, so we are going to talk about visualizing functions. So what we're going to be looking at is sets. First, I'm going to tell you what a graph is. Maybe you think a graph is like two sticks to represent axes and some squiggly curve that sits on top of it. The formal definition of a graph is the combination of the inputs and outputs of a function as a set. So the graph of f, if we imagine we've got a function f that takes a domain x into a codomain y, the graph of f is the set of points x, f of x. That's weird because it means these points live in a space called x cross y. The first coordinate comes from x, the other coordinate comes from y. So this is an abstract way of writing this idea down. If your function f went from R2 into R, then the graph of f would be the set consisting of points x, comma, f of x, but where x comes from R2 and f of x comes from R. That's really a cumbersome way of writing things if we're going to compute. Elegant from a vector perspective, right? Because what this says is, even if this was like R1000 and there were 1,000 coordinates in any vector, I can treat it as just a single entry, a single input. So this is called vectorized notation. To work in practice, instead of using vectorized notation, what we usually do is think of you guys. So this notation, where we have two inputs, x and y, and one output, f of x and y, is the same notation as this. This is the input vector x. This is the output vector f of x. And this dude right here is like the input vector x, and this output is f of x. It's important that you get a handle on how this language works, because a lot of high-level presentation of science, engineering, and of this sort of vector math in mathematics is written in the vectorized language and not in the component language. Okay, so the problem is, how do we draw one of these things? And that last time, I know I totally impressed everybody by drawing a hyperbolic paraboloid off the top of my head, but how did I do it is the question, and that's kind of what I want to show you here. So let's try to think about how we might draw something like, let's pick an easy one. How about z is equal to x squared plus y squared? So I want to draw the graph of f. I want to draw this set of points where x and y were chosen freely, and I compute the z coordinate by evaluating f on x and y. And I don't even know how to begin. So deep in people's memories of multivariable calculus, you might have some remnant of the techniques that you use to approach something like that. And I'm curious if anybody knows any of the technical names or an idea of even how to start. Besides, go to Desmos and stab it in and see what Desmos says that it is. Yep. Level curves. Okay, that's a great idea. So we should define what a level curve is. So a level curve of F is the set of points x, y in R2 that solve k is equal to f of x and y, where z equals k is constant. The definition of a level curve. A level curve is you basically picking some height z and saying, what are all the x's and y's that produce that point? So you've seen this every time you've seen like a pressure map or a topographic map of a mountain, right? What you're expecting to get out the other side is, here's x, here's y. If I draw you something like this, and I say these are level curves, I'm telling you every one of these values or these curves represents the x's and y's that represent a different height. And so when you look at a map like this, the way that you interpret it is, well, I can look at how things are growing or shrinking by how quickly these lines are next to each other and what the overall shape is. So when I look at this, I think, okay, I've got a flat bowl with this weird irregular edge. And as I go out, it starts to curve up, or maybe it just slopes up. But that's what this set of level curves would represent, a flat spot in the middle. And then the heights, remember these represent z values. They represent z values. The heights increase as we go away. So one way of approaching what a function might look like is to say, okay, let's look at the level curves. So let's calculate some for our function instead of this like map of an inverse, like it's a line, it's an upside down number. So for us, a level curve would look like this. K is equal to x squared plus y squared. That is the level curve for z is equal to k. Doesn't make any sense to put a negative number in for k. Well, no, right? Two squares added together are never going to be negative. So k is less than 0. There's no curve. What if k equals 0? If k equals 0, you get the equation 0 is equal to x squared plus y squared. As one point solution, right? The only solution to that is the point 0, 0. So this is not much of a curve. All right, so let's go over here. We'll record our level curves. Okay, there's 1. K equals 0. Let k equals 1. Circle with radius. All right, yeah, so required is that somehow that like ancient algebra knowledge of how to read the conic sections off is going to be important in here, right? This is a circle of radius 1, so the k equals 1 curve is like this. 1. K equals 1. How about k equals 2? Circle of radius root 2. 2 is equal to x squared plus y squared. That's a circle of radius root 2. Okay, so if I did that, I'm going to get something. If this is 2, well, I'm not even to 1.5, right? I'm like here. And if I did k equals 3, I get root 3 radius, which is 1.7. And then for k equals 4, I get radius 2. So the level curves are circles. And what does it mean that these lines are really far apart and these lines are really close together? Steeper, right? I mean, smaller distance to change the same amount of height. The reason I'm picking the height up one at a time is so the height changes are all equal to each other. So what I'm saying here is it took this long to change the height 1 from the starting point out to this first ring. But then, even though I've drawn it really terribly, these rings start to compress into each other as you go out, which means as you get away from the origin, things are starting to grow faster. Great. Well, I've got an idea of what this thing looks like already, but there's another tool we can use. So already from here, you can take a stab at what this thing looks like. Any guesses? So I see. So you did this, and you did a paraboloid that's been rotated. Did you have the same answer or different? Okay. So paraboloid is the name of what this thing is, right? This is called a paraboloid because it is. It's a parabola that's been twisted around an axis. So your guess might be from the level of curves, and you can't always trust level curves because they might be missing information, right? We chose to move up by height 1 each time, but what if it's like really wiggly and squiggly, but the amplitudes are smaller than 1? It could be horrendously oscillatory between 0 and 1, and we never see it, right? But our guess right now is it looks like this. It seems to be what people are telling me. So I want to point out that another way of using these level curves is instead of just viewing them as in art. So this is called a level curve because I've crushed it down to a 2-dimensional visualization. Another way of using the same curves is as what are called contour curves instead. So a contour curve uses the same information, but gives it the correct z value. So a contour curve is in R3. So you find the set of points x, y, so that k is equal to f of x and y. And then you use those x and y values to generate what the curves look like on the surface. So this single point was at z value 0. So here's the contour curve that goes along with that. That's the k is equal to 0 contour curve. At height z equals 1, that was this circle. Well, there's a circle at z equals 1. There's a different circle at height z equals 2. And another circle at z equals 3. And another circle at z equals 4. So you can imagine the contour curves are just the level curves, but like accordioned up to actually sit on the surface. Okay, what else? What other tools do we have? We mentioned this last time, I think. Yeah. No, we're going to definitely do partial derivatives, but not quite yet. Partial derivatives we're going to use to study how quickly we're increasing or decreasing. Yep.
The same way we hold z constant, hold x, hold y.
Do you remember what that's called?
I don't remember what it's called. Is it like sideways level curve?
Yeah, so these are called sections. So sections of a surface are the pictures that you get if you slice through them not this way, but top to bottom with various points. So it's sort of like if you treated it like a loaf of bread and cut it like this. So the x, so you can imagine, yeah, so you can hold, if you hold x is equal to k constant, then what you're doing is you're saying, okay, for different values in this direction, what would the graph look like? So you imagine you take that thing, you cut through it with a plane from the top, and you look at the shape that the surface makes on the plane that you cut through it with. So you should imagine going in that if you do that, what's going to happen? If you took this plane and you dropped it through the surface like this, you should imagine that what you would see would be a shape that looked like this. And every plane that you drew would have a different looking parabola on it, right? They'd be located at different heights. They'd move around. But what I'm saying here is that, like, if you cut through, you would get that shape. And if you cut through over and over and over again, this is actually not the x traces, these are the y traces. But if you cut like that, you're going to get a family of parabolas that start up here, and the vertices would slide down and then go back up again. So if you hold x equals k constant, you get what's called the x equals k section. So that would be z is equal to k squared plus y squared. To me, that looks an awful lot like a family of parabolas. If k is equal to 0, you get z is equal to y squared. That is a parabola that looks like this. And what we've done here is we said, okay, we were at this point right here. We're at this point right here. So we're getting the parabola that defines the outer part of the shape. If I set k equals 1, I get z is equal to 1 plus y squared. What did that do? What do I add 1 to a parabola? What did it do? Translate it up by 1, right? So when you're doing the sections, it's typical to write the height of each particular section that you're studying here. Is it different if I use k is equal to -1? Well, that'd still be z is equal to -1 squared plus y squared, which is still 1 plus y squared. So there's symmetry here. What that's saying is, as you slide to the left and the right, you get the same shape, which is an assertion of symmetry in the figure. So that's k is equal to plus or minus 1. And if you keep going, you'll get more and more of these. What that's suggesting is that as you move this direction, you have this parabola, and it doesn't change shape, but it slides up as you move in this direction and slides up as you move in this direction. That corresponds to, if you imagine taking that parabola and sliding the vertex around, you would get precisely this kind of thing, where you have a parabola, and then another parabola, and then another parabola, and another parabola. Like, this is an aid to figuring out what a shape looks like. You can't ever see the whole thing, but you can look at its images on planes. Yep.
I'm kind of confused as why did we actually set z equal to k over here? I understand kind of why we set k equal to x over here, but I don't understand why.
So the big picture with z is equal to k is you can think about z is equal to k as the z section. We're cutting through with planes that go this way when we're setting z equal to k. So setting z equal to k means we're chopping it up this way. Setting x equal to k means we're chopping it up like this. And setting y equal to k means we're chopping it up like that. So it's just, it's got a different name because we're going to compress it down. But the idea is exactly the same. We just cut through the surface with planes, and we look at the shapes, and then we just plot them all in the same graph. That help? Cool. Okay, so that by itself, the fact that we've drawn the level curves, we drew this family of parabolas that describe what happens if we cut through it one way, and if we cut through it the other way, we get another family of parabolas. So if you set y equal to k, then you end up with z is equal to x squared plus k squared. That's the same family of parabolas, right? You're going to end up with k is equal to 0. It's going to give you this one. And then k is equal to 1. It's going to, or minus 1. It's going to give you z is equal to x squared plus 1. So this one corresponds to both k is equal to plus or minus 1. And this one corresponds to k is equal to plus or minus 2, and so on. Okay. And the idea is that this information, this is how, in the days before computers, especially, this is all you had to work with when you were visualizing these things. You had to build them up by thinking about them in these pieces and trying to stitch together what was going on by thinking about the information you got by cutting through it with planes that go this way, cutting through it with planes that go this way, and cutting through it with planes that go this way. The best you could do is sort of look at the shadow of the shape you were trying to plot, right? So the reason this is still useful now is not because people sit around plotting hyperbolic paraboloids, although that's an amusing exercise to plot a hyperbolic paraboloid. Yeah. But the idea of looking at contour lines and level curves is still used constantly in the analysis of functions. In like, if you think about a physical system, and this isn't some arcane technique of the past. It's, if you think about the sorts of things that show up like this, like, for example, if you're not a mathematician, but you're some sort of scientist, this might be the strength of an electric field, right? At at some point, X and Y in a plane. And what you're doing when you plot things like level curves or contour lines is you're describing all the different ways in which you can picture the field changing as you move around in your location. This comes up all the time in fluids as well. All kinds of physical applications or a temperature map, right? And a temperature map, you might have T is equal to F of X and Y. The temperature distributed across some surface depends on where you are on the surface. If you start drawing level curves, what you're drawing is, these are isotherms in the study of temperature, right? An isotherm is a level curve of the function that defines the temperature. If you're in a field theory, these are called equipotentials instead, right? So these things have not just died because of computers, but the computer will give you this picture. We haven't got rid of these pictures. We want to keep them because visualizing the way that a field shifts is hard to do if you look at a formula, but really easy to do if you look at the way that it distributes itself in terms of its level curves. And so this idea of level curves is not going to go away. We're going to continue using it as we study these functions because the calculus that we're going to do is going to involve these as well. One of the facts that I don't know if you guys remember or not, but it turns out to be the case, even though I haven't told you, and I will not tell you quite yet, or probably 2 more lectures, what the gradient is. Does anybody remember the relationship of the gradients and level curve? So remember, the gradient represents the derivative. If you imagine there's some function that's assigning values back here, and these are all the places where maybe the function is constantly equal to 10. And these are all the places where the function is constantly equal to 8. And you want to know how fast the values of the function are changing. Yep. Yes. It is the steepness, but there's a name for this. So the gradient is this. So what the gradient vector, this derivative vector, if you've seen it, and everyone here has seen the gradient before in some context. What the gradient does is it actually is perpendicular to all the level curves. So the gradient vectors, the idea of the derivative here is that this derivative is deeply tied into the level curves of a function. So the derivative, this particular type of derivative is going to end up being perpendicular to the level curves of a function, which means the way that things change the fastest is to move directly away from where things are constant. So if you're constant in this direction, like you are locally here, right? If you keep sliding along this line, if this was a hill, you would always be at height 8 as long as you stayed on the line. How would you figure out how to go up the fastest? You'd say, well, I'm constant this way, and I'm constant this way, and that's the perpendicular direction, so I'm going to go that way, and that's guaranteed to be the direction of maximum change. Okay, so the level curves are a deep geometric idea and not some leftover thing about plotting functions from 1670. Although they are also left over from plotting functions in 1670. All right, so I want you guys to have a good fake weekend. And those of you that are on the College of Business schedule, enjoy your long weekend. And